So today I'm just gonna share my work on improving the storage stack to be more predictable and efficient, especially under a software hardware co-design approach. So let's get started. Oh, a second. Oops. Yeah. So many services today that we use on a daily basis store their backend data in cloud data centers. And at the backend, we rely on the storage stack to manage the hardware as well as satisfying various user demands. For example, the reliability, security, availability, and quality of services guarantees, and so on. Among these requirements, so predictable performance and efficiency are two main driving factors for the success of modern cloud storage. And on the performance front, high latency can cause severe consequences. For example, Amazon reports that every 100 millisecond latency would cost 1% in sales. And 100 millisecond delay in web page loading time would lose 7% of the users. So similarly, Google has observed that half-second in search page generation time would drop traffic by 20%. So even worse, in high-frequency trading, a broker might lose $100 million just for one extra millisecond latency. Thus, offering low and stable latencies is very important. Furthermore, cloud providers not only want their services to run fast, but also efficient at a low cost. In large-scale data centers, we know that even very small improvements in CPU efficiency could save millions of dollars. And this has recently motivated Google, Microsoft, and other hyperscalers to seek to deploy new software and hardware technologies to squeeze more efficiency out of their highly optimized data centers. So the need for both low and stable latencies, as well as CPU and cost efficiency never ends. Overall, there are new certain challenges to design and build high performance and efficient data center storage systems, especially for modern storage hardware. Why? Well, the world of storage is changing rapidly in both software and hardware. And maintaining high end-to-end performance in an efficient manner is becoming more difficult. Specifically on the hardware side, with the rise of I/O and computation acceleration, we have seen a new brand of new hardware devices that gives us new capabilities, such as much higher performance delivered by modern NVMe storage, as well as the extra computational power from accelerators. Unfortunately, this hardware also comes with a downside. So they are making today's computing landscape more complex by introducing heterogeneous architectures and due to many of the idiosyncrasies associated with today's hardware designs. But we try to rely on the software stack to deliver all these hardware benefits and manage all the hardware complexities. But unfortunately, if we look at the software side, it is not really keeping up with the hardware trends. So today we are still relying on the decade-old interface and abstraction designs, which gives us a very deep storage stack implementation. As a result, what we see is there is a widening gap between what the hardware promises versus what the software is able to extract. So it gives us very high unpredictable latencies as well as very high overhead. Well, for example, let me give you a few more concrete examples here. So to serve ultra-low latencies, today cloud providers have upgraded their storage hardware with fast SSDs capable of processing millions of IOs per second at sub-100 microsecond links. On the network side, today's SSD designs still suffer from idiosyncrasies associated with NAND flash management, so making it hard to deliver consistent performance. On the software side, we see that software stack is becoming more feature-rich due to increasing user demands. But in the meanwhile, the deep storage stack is increasingly becoming the new performance bottleneck. And all these make performance predictability challenging to achieve. Today, this heavy and complex storage stack mainly runs on CPUs. Now, with the shrinking CPU and SSD performance gap, so the CPUs really have to work much harder to get the performance out, causing the stack to be inefficient. Ideally, cloud provider would prefer to reserve these CPU resources to run customer workloads. And for cost efficiency, they have recently started looking into acceleration coprocessors, for example, ARM system on chips for common task offloading. Well, while existing accelerators are good at offloading simple and fixed functionalities with cost efficiency and high performance, well, they cannot retarget end-to-end cloud storage stack, especially under very stringent high performance goals. And this makes resource efficiency challenging to achieve too. So due to the increasing complexity in both storage functionalities, as well as I/O and acceleration hardware, an optimal solution cannot really be easily achieved by just looking at the software or hardware alone. Thus, in my research, I advocate a software-centric co-design approach to revisit the communication interface between the software and hardware, as well as the responsibilities between the two. In particular, my software-centric co-design scheme advocates enhancing existing hardware designs and interface designs with very minimal changes in order to facilitate upper-level software system designs. For example, on one direction, I advocate that the hardware that exposes necessary information to the software to bridge the semantic gap for better system-level policy designs. So in one of our work, we allowed the software to query SSD's internal idiosyncrasy status, and this can significantly help us achieve more stable latencies. On the other direction, I think that some software functionalities are better pushed down to the device for overall cost efficiency. But in the meanwhile, for performance reasons, we might need to define new hardware properties based on the software needs. So at a high level, my research looks at different layers of the storage stack under different hardware contexts as shown in the x-axis. My research specifically tries to make better use of existing hardware, as well as enhancing them for more efficient software system designs. Many of my work have also generated the real-world impact. Here, I will just give you a brief summary of my past work where I made significant contributions to either as first author or as second author. So my first line of work introduces a holistically designed flash storage stack that gives us predictable performance. Specifically, I introduced new interface designs to enable powerful host operating system and SSD co-designs, which gives us always predictable and low latencies. And this work has already attracted some interest from flash array vendors for potential integration with their high-end flash array products where low latency is key. At the hardware level, I revisited the SSD controller architecture designs by leveraging new hardware advancements for more fine-grained I/O management. And for the novelty, this work has been nominated for Best Paper Award at FAST 2017, and also fast-tracked for extended journal publication as a research highlight. At the operating system level, my research looks at how to transform existing operating system designs to be service level objective aware instead of just relying on decade-old best effort scheme. And part of my efforts and findings in this work has already been merged to the Linux kernel open channel SSD subsystem, and it has potentially benefits many other users. For cost efficiency, my second line of work looks at how we can better leverage emerging acceleration and interconnect technologies to improve the storage and memory management in cloud scenarios. So I co-designed the hypervisor and ARM coprocessors to deliver an off-the-ready cloud storage stacks design that can portably run either on x86 or ARM. And with a set of OS and runtime optimization techniques, we can satisfy various data center deployment requirements. And this work has already been deployed in Microsoft data centers to serve production workloads. And in another of my most recent work we introduced the first computer express link-based full stack memory disaggregation design. So it can significantly improve memory resource utilization with very minimal impact to the performance. So lastly, to foster software and hardware storage research, so we need good research platforms. To this end, I have built FEMU and QEMU NVMe-based emulator. So FEMU is very popular among the storage research community. It has been used by hundreds of institutions worldwide. And it has also enabled many recent papers that appear at recent top systems conferences such as OSDI and SSP. So in today's talk, I'm gonna mainly focus on two recent works of mine, YODA and Lipio, which best exercise my co-design principle. And then I will wrap up discussing my future research. Okay, so before I move to the first piece of work, any questions at this moment? Okay, let's continue. So let's start with YODA, a software hardware co-design to achieve predictable latencies on modern flash storage. Well, but first the question we want to ask is, why do we see unpredictable latencies on modern SSDs and how bad it is? Well, SSDs consist of hundreds of NAND flash channels that's connected to a controller. And this controller runs the flash firmware to manage all the backend I/O activities. And for normal I/Os, they will usually see a latency of hundreds of microseconds at the NAND speed. And due to the non-override support by NAND flash media and many other constraints, the flash firmware needs to manage many other background operations, such as garbage collection, wire leveling, to maintain the SSD in steady state. And what the garbage collection does is really simple. So it migrates data internally across different NAND flash channels and chips to reclaim more space. But this will unnecessarily cause more load internally. And when a user read get unlucky and it will potentially contend with garbage collection, and it might suffer from a tail latency of tens of milliseconds, so which is already 100 times worse compared to the base case. And due to the black box nature of existing SSD designs, users do not know when GCs will happen, and they have no controls over them at all. Well, there are many efforts to tackle this garbage collection induced tail latencies associated with NAND flash across different layers of the software hardware stack. So you might wonder, why cannot we just come up with an ideal SSD controller design that gives us always low latencies? Well, many people have exploited the new policies such as fancy preemption, scheduling, and isolation schemes, but they cannot really eliminate all the GC impacts because they cannot solve the blocking nature of garbage collections. At the operating system level, we have also seen some evolvement onto making the software stack to be flash aware. For example, flash aware file system designs and polling-based driver designs. But unfortunately, all these optimizations cannot really tackle the tail latencies that originated from the device. Well, even more aggressive approach is to directly manage the flash from the host side. But this approach is non-trivial to achieve because of many NAND flash management complexities. And it is also incompatible to many of today's applications that rely on traditional storage interface. So YODA advocates a host operating system and a co-design approach to tackle this problem. Specifically, YODA doesn't require a major firmware level policy changes, but rather powered by a very small interface change, so it can give enough information to the operating system level for policy designs to cut the tail latencies. And all these changes are application transparent, so there is no need to for any kind of application code changes to benefit from this design. So YODA is designed with the following goals in mind. First of all, we want very strong latency predictability guarantees at the per IO level. So the figure on the right-hand side shows the latency CDF, and the X represents latency in milliseconds, and Y represents the percentile. So with the red line, you can see that under the default case that with GC, the tail latency can be very bad, especially at high percentiles. Well, ideally, if there is no GC, you can see from the gray line that it is almost just straight, showing that there is no tail latency at all. So the goal of YODA is try to push forward towards this ideal no GC scenario. While we focus on performance predictability, so there are also many other abstract aspects that we want to focus on. Specifically, we want our design to come with minimal device changes, because modern SSDs has already been developed for after years of optimizations for their flash firmware policies. So we definitely do not want to change those. But we also want resource efficiency in terms of both CPU efficiency and not burdening the SSD device with too much extra IOs. And finally, we do not want to sacrifice throughput in order to achieve higher performance. So here we target an ambitious goal to target both. And when compared YODA with many state-of-the-art approaches, so YODA can give us very strong and low predictable latencies without sacrifice performance in an efficient manner. So it only touches the flash firmware a little bit for interface changes, while it can target in a very easy deployment for data center scenarios. At the bottom, so YODA builds on top of this idea to leverage redundancy for performance. Specifically, this is an idea that has been demonstrated quite effective in different scenarios. For example, in error-coded storage systems or replicas in distributed systems. So what it works is basically, if one IO is slow, we can send extra copies of this IO to its replicas or to the parity, not to just wait for the slow IO. However, while this idea is simple and straightforward, it's still challenging to apply it to the SSD design scenario. And the key question that we need to answer here is when to exactly should we issue this parity read or extra reads? Well, you might wonder that similar to the case in distributed systems where you have speculative execution to tackle those struggler problems, here you might want to wait for timeouts before in IO you detect some IO is slow and send an extra read. But it is tricky to pick the timing threshold here. So millisecond level wait is definitely too long for microsecond level IO operations here we target. Well, you can also go very aggressive by proactively sending full stripe reads to the entire flash array. But this approach will increase the load to the SSDs even when they are not busy with garbage collections. And the semantic gap we see here is that the host and SSDs are not able to communicate about the device level business, says existing approaches may heavily rely on guessing, so making it too lazy or too aggressive. To bridge this gap, YODA advocates a fail if slow SSD interface to bridge this gap. So we require the SSDs to tell the host whether an IO will be delayed by GC or not, and if so, fast fail this IO back to the host on purpose. Here is an illustration. So the host submits requests that are tagged with a special latency sensitive flag. And after the SSD receives the request, it will quickly check whether this IO will contain with potential GCs that are going to specific NAND flash channel and chips. And if so, fast fail this IO as soon as possible back to the host without actually executing this IO. And upon receive this fast fail signal, the host side can decide to proactively send parity read to reconstruct the IO. This way, we only need to reconstruct IOs that are known to be slow. Let's see how it works in a, say, RAID 5 setup. So here, suppose that we send down 4 stripe reads to the array. And now let's see. Well, if SSD is busy with GC in this case, so it will quickly fast fail this IO back to the host. And when the host receives this fast fail signal, it will proactively send another parity read to the parity drive. Now, suppose the first 3 SSDs are not busy, then after about 100 microseconds, well, all these 3 sub-IOs will normally return. And with this, we can reconstruct the data using XOR operations. And with this kind of reconstruction, we already have all the data that we need, so this user IO can be safely deemed as completed and returned back to the upper level applications. As you can see, this approach can bring us a very large performance goal, again, with very small overhead. Transferring this kind of fast fail signal through PCIe bus only takes less than 1 microsecond, and reconstruction will only take less than 10 microseconds. So compared to the 10 milliseconds tail latency caused by garbage collections, we have a huge win here. Let's see how well this technique works for a TPCC workload. So here we show the read latency CDF. So the red line is the base case with GC. And as we can see from the dotted orange line, so it can help improve the tail latency a lot by pushing the line to the upper left. For instance, we get roughly about 7 times better latency at the 95th percentile and 5 times at the 99th percentile. Overall, this technique can help us cut tail latencies up to the 99th percentile. You may wonder what's wrong with the last percentile. But let's measure one level deeper. On the right, we plot the number of IOs being blocked by different number of busy SSDs. Specifically, if X equal to 2, then the bar represents the number of IOs that experience 2 concurrent GCs in 2 busy SSDs. And we observe that this fast fail interface can only help with the case that we have only 1 busy SSDs. And in general, that's why we still see a large performance gap towards the no GC ideal case. In general, given K parity blocks associated with in-data blocks, we can tolerate at most K busy sub-IOs or K busy SSDs. And for RAID 5 scenario, K equals to 1. Well, let's take a closer look at why proactive reconstruction won't work with concurrent GCs. Suppose when 2 SSDs are busy, here we might have one of the first fast failed IO trying to trigger the parity reconstruction process, but this time reconstruction won't work because we need to wait for SSD 2 to return its data back, but this time SSD 2 is busy with GC as well. And a better intuitive solution to tackle this problem is say, okay, why don't we wait for the less busy SSDs, and we could still save some latency by doing reconstruction there. But the problem here is that we don't really know how long each SSD will be, how long each GC will last in different SSDs. So as a random wait approach might end up waiting for the busier SSDs, giving us longer tail latencies. And to handle this, YODA advocates to extend the interface a little bit more to communicate about the device level business. So in particular, the SSD knows exactly how long an IO will be delayed by GC, since it orchestrates all the IO activities inside the SSD controller. So along with the busy signal, we can also piggyback the busy remaining time caused by GC. And with this kind of information, the host can decide to wait for the less busy SSDs. And this way, we could still save some latency by performing proactive reconstruction from the less busy SSDs. Here's the result of this new interface with busy remaining time exposure. As we can see from the blue line, so it can further help compared to the previous technique by shifting the line to the upper left a little bit. But we still see a large performance gap towards the no GC ideal scenario, as shown by the shaded area. And the problem here is that we still need to wait for at least one GC to complete before we can perform the proactive reconstruction. And in another scenario, if multiple SSDs are busy for a similar amount of time, this approach won't help either. So the question is just about, can we do better to push towards further close the no GC scenario? Well, to ensure proactive reconstruction will always work, we need to create a case where at most one GC is happening at any time point. But is it not possible? Well, the answer is yes. So we can schedule the SSDs across different time windows to perform those background garbage collection in turn. This way, within each time window, we only see one busy SSD. And this will guarantee that our proactive reconstruction will always work, thus we can get always predictable latencies out of this. And considering that time window is a fixed value, so each SSD can track the time window rotation manners by itself with minimal changes, with minimal coordination needed across multiple devices. But there is still some problem here. So how long should we safely set this time window length to be? So imagine that if we set the time window length to be indefinitely long for one certain device, then it will inevitably prevent other devices from this array to start doing GC. And this will make them bear the risk of running out of space. So there must be some upper bound value for this time window in order for this kind of scheduling mechanism to safely work. So the ideal case is that for any device in this rotational manner, that we should have enough space in the SSD in order to absorb all the incoming write traffic. Let's consider a general case here. So here, the write traffic could keep coming for all the time windows, but for one specific SSD, it is only allowed to perform background garbage collection activity in one time window, along with the remaining overprovisioning space. So we can get something similar to this, which can be further expanded as this complex formula. It gives us the upper bound value of the time window. But with this, the flash storage vendor could program their SSDs with this certain time window in order to make those the previous scheduling mechanism work without breaking the stability guarantees. With all these techniques combined, so we can see that YODA line is almost overlapping with the no GC gray line, and showing that there is no tail latencies here. And YODA can really help us close the gap between the base GC case with the no GC ideal case. Furthermore, YODA also doesn't sacrifice the array's aggregate bandwidth. So as shown on the figure here, so under different mix of read and write workloads, we can see from the green bar that it can achieve similar throughput as the base case. In summary,
question.
Sure.
This is a little counterintuitive because when you do a parity read, you use 3 times as much bandwidth than normal, right? So how come you don't lose any aggregate bandwidth?
Oh, the bandwidth drop here is compared to the base RAID 5 setup. So we are still losing, probably one drive in RAID 5 scenario, but that's not the case that we are trying to compare with here. Making sense?
Well, you're doing more reads that require parity than the normal RAID 5.
Oh, yeah, sure. Yeah, so basically, from the YODA interface changes, we are trying to minimize the number of reads, reconstruction reads that we send down to the device. So as we only observe at most, 6% of IOs being sent down to the flash array. So that's why, overall, it won't affect the read throughput a lot. As you can see from here, so basically the throughput drop is very minimal. But for the write throughput, it's a little different. So writes in RAID setups can involve many internal read operations, which can potentially benefit from the YODA design. So as for read, mixed with the write scenarios, we see that the throughput on the YODA is actually better compared to the base array setup. Did I answer your question?
Yeah, thank you.
Okay, thank you. In summary, YODA is a host SST co-designed to bridge the semantic gap for performance predictability. So powered by a simple fast-fail interface, it can perform predictable and proactive reconstructions with the time window mechanism and the busy remaining time interface. YODA not only advocates co-designs between the host and the device, but also across the different devices to achieve the performance goals. So just as its name suggests that just like the YODA master, YODA, the system here, is also small in size, but very powerful in delivering predictable performance. Okay, YODA gives us low and predictable latencies. Now, let's move on to look at how we can build cost-efficient storage stack on top of emerging accelerator hardware, for example, ARM coprocessors. Today's cloud storage stack is extremely heavy, and it poses a very heavy operational cost. So the servers in cloud data centers provide a large array of x86 cores, and in part, all these cores are ranged to the users to run various types of user workloads, for example, analytics, ML, etc. And the cloud provider charges the users for the amount of resources that they use, thus making revenue. Unfortunately, the cloud storage stack takes away many precious CPU cycles. So on the one part, we need to fulfill many storage services that's required by the users. And on the back end, the deep storage stack also incurs a lot of CPU cycles. Now, all these form the cloud storage tax. As a result, about 10 to 20% of CPU cycles in modern data centers are specifically burned for running the storage stack. And this is a heavy operational cost that cloud providers have to pay. Ideally, the CPUs are better spent to run customer workloads for revenue. And one intuitive solution is to start thinking about offloading those cloud storage stack to modern accelerators. But the first question here is just thinking about which acceleration hardware we should use. Well, given the observations that ARM coprocessor is being increasingly deployed in Microsoft and Amazon AWS, now we have seen some opportunity here for general purpose cores offloading for storage stack. And specifically from the cost perspective, ARM system on chip total cost of ownership is only about $100 each year. But if we could save those CPU cores and rent to the users, we can potentially make $2,000 each year. So this gives us a 20 times, better revenue savings. So here I will present Lipio, a next generation cloud storage stack that is offload ready to ARM coprocessors. So just like traditional cloud storage stack, which help us manage all the backend hardware devices at the hypervisor level and provide those various storage services to the upper level user VMs, Lipio stack fulfills a similar goal, but it can possibly run on x86 and ARM cores to serve those purposes. And Lipio can significantly improve the resource utilization without sacrificing much performance. Okay, so you might wonder why ARM system coprocessor is a big deal here. Considering that we have similar programming environment, we can run general purpose operating system and the storage stack there. So why it doesn't work natively? Well, this is related to the nature that ARM coprocessor sits on the PCI bus and it doesn't have all the power that we have on the CPU side. And this actually caused a lot of challenges in designing and building Lipio. So specifically in data center scenarios, we also need to target various deployment goals that in order to make the software portable. And for this purpose, we need to be able to mask up the low-level hardware complexities. And for this, later on, I will briefly discuss how we achieve this, how we solve this challenge. Furthermore, in cloud scenarios, we also want simple composability across different type of services. But in the traditional way of layering different self-storage services on top of each other triggers a lot of overhead here. And we need to figure out new ways in order to achieve efficient and lean software stack to achieve the composability goal. There are also many other challenges, especially on the performance front due to the resource constraints and in many broken interface designs between the host operating system and the SOC. And for this, later on, I will introduce how we can better leverage a unified address space to reduce the number of data copies to achieve high performance. And finally, clouds evolve at a very fast speed. So we need extensibility in order for the cloud developers to come up with new storage services at cloud speed. And for this, traditional operating system or kernel-based storage service development is hard to debug and it takes a very long time. And for this, we need to carefully think about how we can come up with user-level runtime system designs in order to facilitate or ease the developers' efforts. But before we tackle all the challenges, so let's briefly work through how Lipio handles I/O. In Lipio, each user can select their own user VM and the block device without any changes needed. And Lipio provides a virtual NVMe drive to the user, and it directly maps this virtual NVMe drive between the host and the ARM. And each virtual NVMe drive will be basically abstracted as a pair of NVMe queue pair, which consists of a submission queue and a completion queue for general I/O processing. Now for high performance, we directly map the NVMe queue pairs across the hardware, the host domain, and the ARM core processors. And if the user decides that they want to access local SSDs, for higher throughput or latency reasons, in this case, we can also directly map the queue pairs between the physical SSD and the ARM runtime environment. So the shaded area basically represents the runtime system where all the storage services will run. And we can come up with various types of storage services that can be consisted or composed as a series of operations on the basic NVMe commands, as simple as a chain of different type of NVMe command processing. This design actually gives us several benefits. So the first is the service extensibility. So we can come up with different storage services on top of the repurposed NVMe interface. So unlike traditional way that is heavy, NVMe gives us very light weight to handle those operations across different layers. So it transforms the traditional layer-based service composing to a form that is flat and lean. The second is it allows us to do cost-efficient polling in order to achieve much higher performance. And considering that the runtime system resides in the user space, so all the data can bypass the host OS for high performance. Of course, since everything here that Lipio presents to the VM sits behind the virtual NVMe interface, so it can give us a lot of flexibility to come up with various ways to better support the virtualization and composition. So here, let's see how we can compose different storage services together. Suppose if we have a case for I/O scheduling needs, this I/O might go through a scheduling service first before it can reach the backend device. Well, in another case, we can basically layer another service on top of the previous service. And before here, specifically, it is a replication service before it can be sent down to one or more backend devices here. Of course, this kind of benefits can be extended, to a disaggregated setup, not just limited to the local core processors. Suppose that if we need to store the data or services from the remote server, so the client runtime can basically forward all the I/O requests to the server runtime system, which runs a very similar environment as the client-side ARM coprocessors. And the server side will basically pose on the NVMe queue pair mapped across the network link. And it can further forward these IO requests, either to its local drive or even further transform this IO and forward them to other servers. Now, let's talk about the first challenge on how we can better solve portability here. So the server configurations in modern data centers are never uniform. That is, on some old generation servers, they might only have very old generation hardware, for example, only TCP NIC, and only very old generation SSD devices. But as time goes on, new hardware will be increasingly deployed to the server fleet, and we will see increasingly new fancy hardware that is deployed. And this will cause heterogeneous hardware setups across all the different server fleets in the data centers. So with portability, what we try to avoid here is the fragmenting the fleet into silos defined by their specific hardware capabilities or software optimizations. To achieve this, in Lipio, the storage stack can portably run on x86 and ARM SOC, so wherever they are available. Thus, it is an offload-ready design. So the users are agnostic to whoever is implementing the backend and cloud storage stack. And to support Lipio to run on x86, so we augment existing virtual machine designs with high-level resource availability, and it can expose a similar abstraction as the ARM coprocessors. With Lipio's portability design, so we can keep the servers fungible regardless of whether they are capable of doing acceleration tasks or not. For example, it gives us a lot of benefits to support various types of backend storage devices across various types of interconnect links, whether it is slow hard disk drive, or it is hard SATA-based SSDs, or the disaggregated and emerging software-defined flash. Furthermore, it is important to achieve high performance, even if we are running on wimpy ARM core. And the problem here is that modern ARM coprocessors are mainly designed in a smart SSD or smart NIC format, where the ARM coprocessor is hidden behind all the NIC controller or the storage controller. Thus, there is no direct communication between the host CPU and the ARM coprocessor. And this makes the IO path inefficient. Furthermore, there are many different software hardware components involved in the IO path. And although we only have one copy of data, this data might need to traverse so different hardware software boundaries, as well as multiple data copies in order to achieve to reach its destination. And to minimize data copy, so we designed a uniform address space that incorporates all the different hardware components into this uniform address space. And it's supported by a unified transparent address translation support, so we can minimize the number of data copies for higher performance. Of course, high performance cannot be easily achieved in the ARM coprocessor scenario without high-level support. So specifically here, we define and design a set of new hardware properties in order to enable the aforementioned performance goals. So first, we need the ARM coprocessor to be able to directly access the DMA engine in order for efficient data transfers for either for QPR mapping or for general DMA data transfers. Second, the ARM coprocessor needs to be able to direct access the IOMMU to translate the VM level physical addresses to the host level addresses. Third, in order to minimize the data copies, the ARM needs to be able to directly transfer data between the SSD and in order to reduce data copies. So here we first evaluate the software overhead of Lipio stack on top of the SOC VM setup. So specifically, we run the Lipio storage stack in the SOC VM and expose a virtual NVMe drive to another VM backed by a data center SSD. On top of the virtual NVMe drive in the user VM, we run regular file IO benchmarks. So here we show the result. So the X represents the number of IO threads being used, and Y represents the throughput in terms of millions of IOs per second. And these blue bars basically represent the throughput under a a random read and a random read mixed with random write workloads. As we can see from the red bars, that represents Lipio. So we show that we can achieve similar scalability under increasing number of threads with very small performance drop. On the right-hand side, we plot the CDF, latency CDFs, and we see that Lipio doesn't really add too much tail latencies compared to the bare metal performance. And overall, the overhead of Lipio is very small, only at 2 to 5%. Furthermore, we run the Lipio offloaded storage stack on a real ARM system on chip. And here we run the FIO and YCSB workloads. And we observe that under this kind of stress workloads, so we see up to 30% performance slowdown due to existing ARM coprocessor design inefficiencies. But we believe that this performance will significantly improve with future ARM clock designs when all the necessary hardware features are ready. To summarize, Lipio is an off-the-ready cloud storage stack design that can help us satisfy various data center deployment requirements, such as portability, extensibility, efficiency, and many others. It brings about 20 times cost savings at only 2 to 5% software overhead. And we also suggested to the SOC vendors with a set of common hardware features in order to bridge the performance gap between ARM and x86. Now, before we move to future work, any other questions at this moment? Okay, let's continue. So looking forward, I believe that we can push the co-design to the next level for both emerging hardware as well as the application paradigms. But specifically, hardware are still evolving very quickly these days. So even for flash storage, we are constantly seeing new interfaces, designs, features that spring up, and they still remain to be explored on how they can better integrate it into existing software systems to benefit existing applications. And on the other hand, we have also seen a new brand of hardware devices that comes with different flavors of storage formats, different type of computational power, and behind these, different vendors are working towards different directions. So one timely direction that I think the system community should focus on is try to figure out what are the proper operating system level abstractions in order for us to better leverage these hardware benefits in terms of both performance and programmability. At the software side, we also see a few major applications that is really taking up the major CPU cycles in modern data centers. And similar to the hardware specialization trends we see today, these days, so I think that we should also think about how we can better support, better evolve existing operating system and storage system designs to better support these emerging applications. So one direction is through system specialization or through near data processing that is powered by computational storage or smart NICs these days. While my current work mainly focuses on the core systems research, I do envision that my future research will be highly interdisciplinary. So being a system researcher, so we can greatly benefit from many ideas that is coming from other areas, as well as we can apply systems approach to solve problems in other domains. Here, I do see a lot of opportunities in order to co-design the storage stack with other areas such as computer networking, architecture, machine learning, database, etc. So here I will briefly go through a few examples. One of my future research direction will explore the interaction between machine learning and the storage systems. So specifically for the storage for machine learning thrusts, we can think about how we can better solve the potential storage bottlenecks that is happening in today's machine learning frameworks. And in another direction, we can also use more machine learning based techniques to come up with better system designs. For example, to improve our current scheduling policies or to enhance our SSD controller firmware policies. And all these combined can help us improve the efficiency and performance of the stack across machine learning runtime, operating system, and hardware levels. There are a lot of opportunity to combine storage systems research and networking. And motivated by the ever increasing networking speed, so we have seen new trends so that will easily allow us to disaggregate the storage and the memory in order to achieve better resource utilization and total cost of ownership. However, there is still a major challenge ahead on how we can better manage this extra latency that is introduced by the networking layer. In another scenario, the edge side shades a different problem. So we usually have very wimpy nodes that needs to collect tons of data, and we need to send them back through slow network to the cloud for the analysis. But there is still this kind of open question: can we ever utilizing computational storage techniques to enable efficient in-place data processing at the edge? And with that, I will conclude this talk. Thank you so much for your attention, and I'm happy to take questions.